Welcome everyone, my name is Ted Young, I work at LightStep, and I completely geek out on distributed tracing all the time. So to start this off, if everyone could help me, just raise your arms in the air and wave your hands. I see a bunch of waving hands, that's right. Because what this whole talk is a hand-waving exercise. And so I want you all to participate in this with me. So I'm going to be throwing things up here, and you're going to be like, oh my God, and just like relax, and just kind of roll with it. We're going to kind of like get a little vision-y here. So first of all, distributed tracing. I kind of presume if you're coming to a trace-driven talk, you already know about distributed tracing, so I'm not going to dwell on this. If you haven't seen distributed tracing before, please pause the video now and go watch a video on distributed tracing and come back. If you're part of our live studio audience and you don't know what tracing is, just think logging. We're talking about logging. There's an architectural model here. The part that I'm interested in is this trace data. So whenever you're exporting your traces out of your system, that has to come out in some kind of data format with some kind of data schema. And I want to explore some really interesting things you could do if you took this data schema and had some standardized way of doing it, something that was comfortable enough something that was standardized enough you would be comfortable reusing this in other environments, like your development environment. So what could you do with this structured data? So you've got traces. Traces have many spans. The spans can be decorated with rich semantic information, like this is an HTTP client, this is a database call, things like that. So imagine a data model like this. This already exists. It's just not standardized necessarily. But that's what we're going to be working with. So how could you take that tracing data that your system is producing and start feeding that into your testing models during development? So the traditional kind of test flow is usually some sort of before, test, after flow. You're setting things up. You're executing some code to test your code, and then you're resetting things afterwards. And we're going to switch that to a slightly different model. It's going to look fairly similar, but it's slightly different. We're going to define our model. We're going to define the tests that we're going to make. Then we're going to gather some data, and we're going to check that data against our model. So let's imagine for the rest of this, we're building a bank. For example, one thing you do with this bank is you want to ensure that accounts can't withdraw more money than they contain, right? I get this is probably not how you actually build a bank, but bear with me. But let's write a test for this. So we're going to hang on this slide for a minute because you're going to see this slide a lot. Now, again, do not freak out about the syntax on the screen. There are many, many syntaxes you could choose to do this style of testing. Any syntax in any language that is functional and somewhat declarative, I would argue, would work for this. And that's actually going to be an advantage that we're going to see going forwards. But this basic idea is, so in this particular case, we're going to create a model. We're going to create a particular example in this model, which is accounts cannot withdraw more than their balance. So we're going to say when you see a span called fetch balance, and it has a tag called amount, and that tag is less than the amount tag on the withdrawal span, then you expect to see a rollback. And you do not expect to see a commit. And you also expect to see a API level span account withdrawal, and that should have a status code of 500. So that's kind of what we're defining to be the behavior for when you try to over-withdraw your account in this particular bank. And then we're going to check that model against some test data. So everyone with me here? Like very basic test. You could write this test in a variety of ways. So how would you then go about gathering this test data? Well, the first thing is, what about a unit test? You want very fast feedback on this bank API. So you might set up your an instantiation of just this in code. You may attach a mock database to it. So we're just going to create a mock tracer and a mock database and create a new running bank API with that tracer and database. You're going to tell the mock database to, hey, always return 300 for the balance. And then we're going to run the withdraw command on the bank server for 500. And then we're going to gather the test data. And then we're going to expect this model to pass if that bank actually refused to commit. So if you had not written code yet to do this math, you would expect to see a commit. You would expect to see this test fail. Then you write that code. You pass this test. OK, so we're working in our little unit test environment. But everyone knows unit tests, these are very, very isolated testing environments. They're not very reflective of reality. So you always want to cross-check your unit tests with your integration tests. So what does an integration test look like? Well, now you're in a local environment spinning up real processes, right? So you spin up your bank server. You spin up a real database, but still like a local, maybe in-memory database, something you can actually run on your laptop. You spin up a trace collector to collect your information. You populate that database with some test data. And then you run your tests driven by the API client. So you spin up a client. You say, get the balance. Then you try to withdraw twice whatever that balance was you got back. And then you fetch your trace data and go have a look at it. What does that test look like? Huh, that's funny. It looks just like the last test I wrote. It hasn't changed at all. The only thing that's changed here is what test data did I get back? This was test data from an integration test rather than test data from a unit test with mocks. But the actual test itself looks exactly the same. I think that's powerful. But let's take this a step further to really see how powerful this might be. Because that integration environment, that integration environment is better than your unit environment. It's more like your production environment, but it's not exactly your production environment, right? Like production is like this huge honking thing you can't possibly run on your laptop. There is a database there, but it's not this like local MySQL database you are using in your integration test. It's some kind of cloud DB as a service thing that someone else is running for you, just massive, crazy thing. You're running lots and lots of bank APIs, lots and lots of clients. There's data and things flying everywhere. There's all kinds of crazy stuff happening. So your integration environment, it's kind of like your production environment, but it's not really. And we all know there's gaps, right? This is why we're monitoring in production to begin with, right? Because, it might be different from what you were doing in development. So what can you do here? Well, one thing we're doing in production is we're collecting a huge amount of trace data. Assuming we have distributed tracing turned on in production, you've got some large-scale tracing, SAS collector, something like this that's collecting traces. Perhaps they're sampled, perhaps they're not. And what would it be to test whether all the assertions you made in development are still holding true in production? Even though you've kind of changed your production environment from your development environment, you'd really like to know your assertions are still holding true. Wow, that's interesting. It's the exact same test. I didn't have to change anything about this test to test against a stream of production data. We're just taking our model, we're running it against a stream of test data, and it's just running assertions on that test data over and over and over again. Nothing has changed. It's literally the exact same test. So I think this is crazy. You can look at remotely executing code and test it the same way you are testing locally executing code. And this is the power of testing with data. Because what we've done here really is, I've kind of pulled a trick on you. This is generative testing. So if you've ever done quick check or any kind of generative testing, anything kind of that test environment where you end up with this sort of purely functional testing, it ends up looking kind of like this. Because you're testing against data, you're really just doing data analysis at this point. So any data analysis tools you have, you could bring to bear against this tracing data. And Isn't that basically just testing? So let's take it a step further. What about formal specifications? I don't know, this is a kind of temporal Lamport logic. I don't know if anyone's ever seen this, but this is an interesting way of ensuring that your distributed systems are actually consistent, functioning the way you expect them. And it's really good stuff, but show of hands, who's ever tried to do formal verification of running system? I see like one couple hands. Like, how much fun was that? Was it hard? Was it easy? Yeah, exactly. The first time you go to do this, and I would argue it's like, I know the squiggly syntax looks weird, but I guarantee you the first time you try to do this, it's not learning the syntax or learning how to do formal verification. I would argue that's like the fun part. It's like, literally, how do I do this? Like, if you go try to set this up in a day, you will be so sad. You will just be so sad because, like, what is this tool chain? Like, what is this stuff? You're miles away from your finish line when you try to do this. You have some kind of crazy tool chain you're trying to set up. You have to learn a bunch of new syntax. You have to define your whole formal logic, all of this very basic modeling stuff that's very far away from your application. And then you're like, cool, I verified this formal model, but wait, what does that formal model have to do with my actual running application? How do I ensure that my application is actually the same thing as my formal model? Okay, I guess I could do something there, but it's going to be pretty ad hoc. I kind of have to make it up. And then once you've done all of that work, then finally you can start making assertions with that and perhaps fixing things. And I would argue the big problem with some of these more quote-unquote advanced techniques, fuzzing, generative testing, certainly formal verification, is that it's just such a slog to get to the point where you're actually getting value and doing work. It's just this huge backlog of stuff you have to do. But what if you did this on top of distributed tracing? Well, you know, modeling from scratch is difficult, but distributed tracing is a very simple, standardized model, right? Like, it's not a model that you have, I see someone like, but it's much simpler. It's a much simpler model than, say, a programming language. Your programming language is a very complicated model, but traces with spans with references to each other, that's fairly straightforward. If you've got standard ways of explaining what an HTTP request looks like, if you can start relying on what some of this data schema is going to be, then you can start building a lot of kind of standardized, proof logic and things like this. Like, what does a retry with backoff look like? You can just model that in a standard way, and then someone else can come along and pick up that standard model, and because the data coming out of your system is standardized, you can check it against that without having to do any of that scut work yourself. So we can all start kind of sharing those parts. The part where reality is separate from your verified model, well, you're going to run this against your actual code. Like, you can now, there's certain parts of model checking with formal verification that might be difficult to run against actual code, but you can certainly create a much stronger feedback loop than you could in an environment where these things are totally separate and it's kind of ad hoc. And the tooling, the environment, all of that stuff, it's the same thing you were doing before. So, like, let's have a look at this, right? I actually did this as 2 sets of slides, my bad. So here's the visual version of what I just said, right? You've got the simple standard model. Reality is extremely similar to that model. You've verified that because you've extracted your model from your reality. And the tool chain, it's the same thing you were already doing. Like, what we're seeing here looks more like generative testing than formal logic, but I would argue that's much more about, what are your primitives that you're working with in this language? Is it less than, or is it some like temporal logic primitive? But I believe you could write this in a manner that looked fairly familiar to programmers without a lot of like math syntax, essentially. So I think that's something that's worth checking out. And now the starting point is much, much closer to where you were before. Like, if all of that tool chain, if all of that work is standardized, you can go straight to making assertions and fixing things. And I think that's really powerful. I think there are some issues with this approach. I don't think it's perfect necessarily, though I'd love to tell you that it's perfect and there's no problems. The two that come up for me that I think are maybe problematic, certainly involve some work. One is, if you're going to test your code based on the tracing data that represents your code, how do you ensure that that tracing data actually represents your code? How do you ensure that if you have a trace point that says X happened, that that actually has a one-to-one relationship with X happening? There's a little bit of work there. I could see small unit tests or something like that, some kind of binding glue to ensure that. But shouldn't we be checking that anyways? If we're going to be relying on this data to monitor our applications, wouldn't you want some assurance that what you were looking at in your monitoring data did actually line up with reality? Isn't this a thing we should possibly already be doing? The other issue that I think is a little tricky whenever you come to something that's sort of purely functional or side effect free is the data you can use only comes from the code you're running. So if you're going to be writing tests in this style, you can't sort of go around back and then check in the database to see, did it really withdraw the amount or not? That's a style of thing you couldn't, you could do that, but you would lose all of this benefits of them being able to go from unit testing to integration testing to production testing. So there's a sort of style of ensuring that you can assert everything you would like to know about your system based on what your system is actually doing without adding an additional non-system component to this test. So I think there's a little bit of trick work that we need to do to get kind of comfortable with that. But at the same time, if you're doing that kind of work, that's just more kind of artificial things. Like when you're in production, likewise, you're probably not going to be able to use those kinds of tricks. So why does this matter? Beyond looking like a neat trick, why does this really matter? From the perspective of observing your system and running it. And I would argue it's really important that we start merging our development practices and our monitoring practices. Right now we have this world where we go develop code and we have all this tooling that we use to develop that code, and then we throw it over into production, and then we want to see what it's doing in production, and we use a whole different tool chain to do that. And we don't test that tool chain in development. We don't utilize that tool chain in development. And I have found over the years that that means that tool chain has a high variance in quality, is perhaps the polite way to say that. Like any code, at the end of the day, you need to write code in order to monitor your system. It's true, automation can help, but it can only help so much. At some point, a human has to get in there and describe what's going on so another human can look at what's going on and understand it. And like any code that you ship that you don't test or have any kind of feedback loop as you're writing it, like the quality is bad. If you were to ship production code and not test it and not really exercise it while you're developing it, like how good would that code be when it runs? Not great. And it doesn't surprise me that logging, metrics, all of these things, it tends to be hard to figure out how you ensure that it's quality data. And I don't just mean logging too much or not enough, but just making sure that what you're putting in there is going to be useful to help you understand what your system is doing when you're trying to figure out what it's doing in production. So quality always suffers in this case. The flip side is like, well, why does this help development beyond being a cool-looking trip? The main problem I see with developing code and trying to ensure that it's correct and bug-free when you ship it into production is that all your test environments are artificial. It's just not reality. And if you could test against reality, I would argue you would do it. You would test against production if you could, and I would argue that we do test against production. It's just the crudest possible tests you could imagine. Like, smoke tests are so crude. They are so coarsely grained in what they can tell you. Just like, maybe there's kind of something weird is about all you can usually get out of a smoke test. SLOs and alertings, those are basically tests. You're writing tests. If latency stays above X for Y amount of time, send me an alert. That is a test. But it's a very, very crude test, often done through some kind of GUI thing, right? As opposed to like programming in text, where we can write things that are very nuanced in a very dense style. So if running your tests against production wasn't hard, I think you would really do it. And if you were triaging a problem and you were trying to figure out which hypotheses you should pursue, you would really benefit from being able to quickly test those hypotheses. So you didn't write the test before, but as you drill down without redeploying anything or doing anything in development, if you could continue to massage and change the assertions that you were making against your production code, I think that would be a very, very handy tool to have in your tool belt while you're trying to dig into a problem. And lastly, I think the main point to take away here is that we've been talking about trace data, like trace data is something special, but really trace data is just data. Trace-driven development is really just data-driven development. There's no reason why you can't take these style of testing that we usually use to test for logical execution in our code and write the same kind of tests against the sort of aggregate data that we collect in production. Resource usage, latency outliers, error rates, anything going on, any sort of aggregate rollup, and you want to start making assertions that has some covariance with something else. These things are not straying from each other. This is not ever going negative. When I have 10 instances, I expect resource utilization to be X on this process when load is Y. Those styles, that style of testing, I believe you could do that against all kinds of production detection tools that we like to use. At the end of the day, we're just analyzing structured data. And we have a huge body of data science out there. There's all these tools out there in so many different languages and environments for analyzing structured data. And if you have a standard model of structured data that semantically describes what your software is doing in production, that is a hugely powerful toolkit. I think that is more powerful in many ways from these more kind of a la carte things that we're doing. And so at the end of the day, this is just to get people thinking about how we can start applying data science to observing our software in a way that's not just making pretty graphs, but actually writing assertions and creating hypotheses and testing them. Okay, so what's next? What do we need here? Well, we need trace data. There are a variety of schemas out there, but they're proprietary in air quotes in the sense that they're often tied to a particular implementation. LightStep has a data schema. X-Ray has a data schema. Jaeger is open. They've got a data schema. So that's stuff, but do you really want to have your whole development toolchain tied to the X-Ray data schema? And how are you going to get things locally to produce stuff in that schema? And I don't know. I would like to see something standardized here. I think that would open the doors for a lot of these things. Conveniently, one other thing I've been helping work on is the W3C Trace Context Working Group. This is a group, I'm sure there's people from this group in the room. I see Sergey over there. Trying to define a wire protocol for in-band context propagation. So, basically standard HTTP headers for distributed tracing, so that when you see traces coming in from another third-party system, you could continue that trace in your system. And the user who's running your collective systems might be able to take trace data from the tracing system in the first leg and trace data from the tracing system in the second leg, and then glue that trace data together to get a more complete view of the system. And I sure have been saying trace data a lot when I was describing that problem. So another thing we've been starting to work on in this working group is this trace data issue, because having that standardized I think would be really great. Okay, that's what I got. Next step to me is just a call of action. So if you're interested in this kind of stuff, you can find me outside later. I think we've got some time for some questions. But I'm going to keep updating on this, something I'm going to keep working on. If you follow me on Twitter and tell me about what you're up to, I will retweet it. I would love to see people start playing with these kinds of trace-based testing interfaces. I would love to see more experiments with these more powerful forms of testing, temporal logic model checkers, and other fun. And on that note, I think we've got a couple minutes for questions, so I'm going to open the floor.
So with the trace data,
oh yeah, yay, yay me. And yay all of you for being interested in this.
I love all this with all the traces and the trace data and the IDs flowing through. What's the worry about privacy protection? Because now you have effectively data that'll tell you this user or this device from this place did all this stuff and caused all this.
Yeah, I mean, I think this is a fundamental issue with observability and privacy. These are like a yin and yang. That data is in your monitoring system if you put it in there. And it's an aspect of privacy that I don't think gets addressed directly too much, but it is something we do need to really think about.
You have to have some way of hiding things that
yes. Scrubbers, things of that nature. But I would suggest that maybe doing this style of testing doesn't necessarily make that problem worse, though we might notice it more.
I think it's, well, the causality following, especially across services with the WPC,
yeah.
could make it worse, because now there's actual visibility in the second tier services.
Yes. What data you actually propagate from service A to service B. I think people just have to be smart and selective about what they're putting in there. And that's just on the developers of those systems to do that. Yeah. You got a question? Thank you. Question back there. Shout.
Shout, you got it. So one of the aspects of model checkers and temporal logic is you need to completely specify your system in order to have a complete and correct analysis. I don't see that completion aspect present in just traces. Can you speak to the static versus dynamic aspect of this and how you can upgrade over to a model checker from tracing?
Yeah. So I think the question was, is there, you're seeing a leap between the model that you get from distributed tracing to the kind of model you would need to do more formal analysis? Yeah. I think that would be an interesting exercise to do, because if we can't do this kind of analysis with this current semantic model of distributed tracing, I would say that indicates a flaw in that model that needs to get fixed. I believe you can, but I also know for a fact that there are rough edges around this current distributed tracing model. There are a number of things that are not present in it at this time that I would like present in it for just even more basic monitoring. You know, the concept of a service that these transactions are ingressing and egressing out of is like a sort of a ghost in the system in this current distributed tracing model, and that's something I would like to fix. But I think that's something we could iterate towards, and I think this would help. Cool. And I think that was me getting played off the stage. Cool. Well, I'll be hanging out outside, and I'll be at the LightStep booth all afternoon if anyone wants to find me there.